On behalf of our team members, I'd like to extend a warm welcome to all friends and family, alumni, industry representatives, Monash University staff and students, and anyone else who's interested in our team's work. For those of you who don't know me, my name's Julian Seedley, and I'm the current team lead here at Monash UAS. In this showcase, we will be presenting our key achievements of the year and reveal what's next for the team. Despite lockdowns, shutdowns, and now earthquakes, we've made great strides in improving the abilities of our aircraft systems, as well as their efficiency and automation. Before we begin with the presentations, I'd like to acknowledge and pay my respects to the people of the Kulin Nations, who are the traditional owners of Monash University Clayton campus, from where I am currently filming. As this is an online event, you may be situated on land with different traditional owners, and I encourage you to reflect on the owners of wherever you are. I also acknowledge the elders, past, present, and emerging, from whom sovereignty was never ceded. Now you'll notice the format of this event is very different from the traditional webinar setup. After this video presentation, you'll be free to move around the virtual workshop and get a feel for who we really are as a team. We're looking forward to your thoughts, so encourage you to interact and ask questions as much as you can. We've tried to make this an event which is not just informative, but also fun for everyone. If traditional webinars are more your thing, I hear that our good friends at HPR have an especially long one coming up soon. Now, without further ado, let's move on with the videos.
This year's Medical Rescue Challenge required us to establish audio and video communication with people in regional areas while they wait for an ambulance to arrive. To combat this challenge, we designed and built two aircrafts. One capable of vertical takeoff and landing, which was to deliver a rover, and one conventional aircraft that stays in the air and acts as a relay. The competition this year was unfortunately cancelled. However, we realised that the relay aircraft we designed might be capable of breaking a current world record.
Our aircraft was designed to maximise endurance, to maximise the time that the aircraft can stay in the air and transmit the feed to emergency services. In doing so, we designed an aircraft capable of flying longer than the current endurance record for under 5 kilo aircraft. The current record stands at 2 hours and 20 minutes as set in November 2020. To maximise our flight time, our team undertook a few projects to reduce weight and drag on the aircraft, undertook thrust testing to select the most efficient motor and battery combination, and ensured that we minimise electromagnetic interference. At this stage, we constructed a test bed that allows for pilot training and autopilot optimization. Our next steps over an 8-week period, when we are allowed back on campus, will be to construct a model on which we can easily test and replace different motors and a final version that will break the world record. So how did we make all this possible?
We've been working on reducing the weight and drag of Local Hawk's wing. Our current wings are made by laying up fiberglass over a foam core cut in the shape of the wing we want to build. These wings are something like 7 to 10 times stronger than they need to be. In aerospace design, we want things to be as light as possible, which means we want them to be as weak as possible with some factor of safety applied. I know that sounds bad, but any extra weight that goes towards increasing strength beyond what we need costs more energy to make it fly. The way we make our wings also creates a seam at the leading edge, which has to be sanded perfectly smooth, otherwise the aerodynamics over the rest of the wing are ruined from the start. We have devised a layout method that allows us to make the skin of the wing without the seam at the front and separate from the foam. This improved leading edge will have reduced drag, which means that the energy that was required to overcome this drag can now be used for longer flight times. Now that we can make the skin separately, we have a lot more flexibility about the internal structure design. Whilst extruded polystyrene is incredibly light, air is much lighter, so we have designed an internal structure that is mostly hollow.
This new construction method would only be adopted if it brought more benefits than drawbacks. The main benefits of this new design are drag reduction, as mentioned before, and the potential for weight savings, with 4 of the 5 designs for internal structures showing a weight reduction. The rectangular spar design in particular has a weight saving of over 40%. The design I have here has a weight saving of 20%, which is made of hollow tubes made from carbon fibre as well as plywood spars. Also, during our test constructions, we have found that the new method of construction is much more simple to construct, since we only need to create the skin, then attach the internal structure at a later time. In future, we are looking to verify the strength of our designs experimentally. However, this has been delayed due to the lockdown. With the new design, it also requires a redesign of our control surfaces, as well as the mounting surfaces for our servos. This is being done concurrently by another team.
UAS's current control surface design features an exposed linkage and hinge slot. Servos are connected to control surfaces by a linkage, generally a simple metal rod, running from the servo arm to a horn attached to the control surface. Analysis on ANSYS CFD found that the straight test section of the wing created 15% extra drag at 0 degrees angle of attack. We aim to take that down to 0.
Our new internal control system fits inside the wing so that there's no interruption to the smooth surface of the wing. This is done by placing the servo deeper inside of the wing, shortening the servo arm, and 3D printing the control surfaces separately from the original foam core of the wing. The new 3D printed control surfaces are extended on the underside so that when the control surface moves up or down, the airflow remains attached, reducing the aircraft's drag. The control surfaces can be printed out of carbon fiber filament or even a fiber reinforced nylon, which weigh little more than the existing skin and foam control surfaces.
The first prototype involved retrofitting an internal linkage mechanism to our current chord wing design and hinging a 3D printed control surfaces. Notice how the mechanism is completely enclosed inside the wing, and the hinge slot remains covered for most control surface deflection angles.
We encountered issues around component access and ease of installation due to the small size of the parts involved, although the design does still fulfill the drag reduction requirements. To solve these concerns, the new Icelandic method for wing design, which you've just heard about, comes in. This new method allows the installation of the internal control system to the internals of the wing before the system is glued on, which will solve the difficulties we faced in installing it.
The next prototype will mount directly onto the Icelandic wing, with a final goal of consistent implementation of internal linkages and 3D printed control surfaces on all of our future planes, leading to more competitive and performant aircraft from Monash UAS.
Now we have a great airframe and construction method. What about the powertrain? The powertrain of an aeroplane generally consists of the propeller, the motor, the speed controller or ESC, and finally the battery. Beginning with the motor and propeller, we had to find the ideal combination where the propeller was producing its thrust as efficiently as possible, and the motor then producing its power as efficiently as possible. There are two variables to optimize here, being prop diameter and prop pitch. These are related together by the ratio pitch over diameter. We can optimize the best P over D and then choose the diameter to have the highest prop efficiency.
Now that we've chosen the propeller, we need a motor. There are literally thousands of motors to choose from, being sourced from all over the world, so it's not a small feat. Furthermore, motor manufacturers all provide different specifications, such that motors are hardly comparable. It's impossible to decide on a motor without a little guesswork, at least not without testing them ourselves. So we decided to test them ourselves.
The thrust test stand tests, monitors and records the effectiveness and efficiency of our UAV propulsion system. This stand records thrust, torque, RPM and electrical power at 2 stages of the cycle. It also has multiple sensors. All these sensors are integrated through a custom-built PCB that interfaces with Tora. With this data, the powertrain can be optimized for a given aircraft requirement. For example, the world record aircraft requires that we fly at the maximum lift-on drag. We now have a reliable platform to accurately predict how our aircraft will perform and make the best decision possible about our UAV propulsion system.
With motors and props sorted, we can now turn our attention to the electronic speed controller. Traditionally, these work by turning on and off power to the motor really fast to adjust the power going in, kind of like a square wave. The inductance of the motor normally smooths this out and it's fine. For this plane, however, we needed something better. We used something called field-oriented control, which basically provides a pure sine wave to our motors. Using this, we can increase efficiency by up to 10%, which is huge.
The last step of this process is to find a battery. In keeping with the theme of innovation with this project, we looked at custom lithium battery packs. These have astonishingly high power densities and are great for our use case of a relatively low power draw system. We were just about to pull the trigger on those batteries when our attention was drawn to a new cell type called semi-solid lithium technology. These have the same energy density as lithium ion, but allow much higher current draws, allowing us to create hybrid battery packs suitable for even our most powerful aircraft, such as our airframe. With such high power draws from our mainframe though, it brings some unexpected issues.
The hardest bugs to diagnose in electronics are those you can't see. Electromagnetic interference, or EMI, is radiation emitted by, well, everything. Devices that draw a large amount of power are especially big generators of EMI. On an airplane or quadcopter, that's the motors, which draw the same amount of power as an average home. So although we can't see it, EMI can be absorbed by our sensitive electronics and completely wreck them, making our planes fall out of the sky. Since it's invisible radio waves, it's really hard to diagnose this problem. Until now. We found uses for our EMI probes in no-contact PCB debugging. By using a really small tip, we can pinpoint exactly what circuit component is generating noise and couple into the circuit to see what's going on.
Using these probes, we revised our avionics stack to optimally shield from EMI. We completely rerouted all wiring for the local hawk, and we finely tuned our antennas to reduce power draw. That last point is especially important for the world record, where we need to reduce power draw as much as possible across our avionics stack. Redesigning the wiring harnesses allows us to eliminate nearly all servo jitter that can waste valuable energy. With all this technology and development, this local hawk is our most advanced yet, and we can't wait to smash the world record.
Our project Gerbil is named after the Bundjalung word for surrounding attack. We aim to create a swarm of autonomous drones that can locate and navigate themselves indoors, are safe to fly around humans, and can get to their goal destination without colliding with other drones. So how do we do it?
Our indoor positioning system utilises new technology, the same used in Apple AirTags, so that our drones can identify their precise location everywhere. We've also implemented our own collaborative pathfinding algorithm, so that drones will never crash into obstacles or each other. Our pathfinding algorithm uses positioning technology to allow our autonomous drones to find the most direct path towards their goal without any collisions. To achieve this, it comprises 2 layers. On the lower layer, the algorithm searches for the most direct path for each drone individually, avoiding known obstacles on the map. As part of the upper layer, the algorithm searches for conflicts between the drones' paths. If a conflict is detected, the algorithm requests that certain drones replan their path before checking again to ensure no new collisions have been created. Once it is sure that there will be no collisions between our drones, the paths are sent out to corresponding drones over our network. We have developed our own graphic interface for testing, enabling us to better understand how our algorithm is running and if there can be any improvements made. This allows us to keep working on our algorithm, continuously trying to improve its efficiency and efficacy.
GPS is an amazing tool to find the position of our drones in 3D space. It's a shame it doesn't work indoors. On the other hand, ultra-wideband technology is an increasingly popular choice in industry for indoor positioning and high-precision locating. We are using it to replace GPS indoors. UWB can be accurate to within 4 centimeters by measuring the distances between the drone and multiple stationary points. So how do we make these stationary reference points?
Well, we call these things anchor nodes, and communication between the drone and the mission controller takes place via these anchor nodes over a network type called thread. The benefit of implementing a network using thread is its ability to repair itself and dynamically respond to changes in the network, ensuring a high level of robustness and reliability.
The PCB for these nodes combines various components, including a module for UWB communication, a module for thread network communication, and a battery management system. Together, these components allow us to form a portable mesh network that has multiple anchor nodes communicating to each other, to multiple drones, and to a central mission controller that facilitates positioning, telemetry, and goal setting for navigation. So we can pick up an anchor node, place it around a drone, and it will automatically detect its position, join the network, and start helping out. The entire setup can be done in under 5 minutes without any configuration needed.
Camilla interfaces seamlessly with Bombist and the inventory management program. Together, we aim to prevent items from being lost and flag items that need to be reordered to avoid delays in our projects. Camilla is easy to use and a clean web app that works alongside Bombist. Using their own account, a UAS member can scan an item to take it out of inventory. Then later, you can simply scan the same part to return it, all from Camilla. This allows us to conveniently take and return items from the compactors, JBS cabinets, or the workshop inventory, all without touching another computer. A common problem is needing to search stacks of drawers to laboriously find potentially 100 different PCB components. With our new inventory management system backed by Camilla, this is a problem of the past. Bombist empowers UAS members to create a custom project, import their PCBs, bill of materials straight from Altium, then generate a custom purchase list of any components not stocked at UAS. This helps our projects deliver on time and on budget. UAS members can select from a range of quotes automatically sourced by Bombist. We can also manage our supply chain to create custom quotes and assign this to custom suppliers we've added. After ordering, this enables us to track a purchase from order to delivery, keeping everyone informed at all times. Once added to inventory, a UAS member can scan these items, scan a breadboard, and be on their way to work on one of these projects.
The new flying competition, or NFC, is a prestigious international competition held in Hamburg, Germany. The competition, scheduled in 2022, has multiple challenging and novel aspects. Our aircraft needs to house a 2-kilogram payload, take off vertically, fly for 10 kilometers, search for and use image recognition to locate 5 small square targets, and then land vertically. The 50-centimeter targets need to be found within an area that's about half a square kilometer, and the location needs to be recorded to within a meter accuracy. All of this needs to be done within 30 minutes. And within that time, the aircraft will also undergo a 2.5G turn. This means that the structure of the aircraft will need to sustain stresses of 2.5 times its own weight. More importantly, this aircraft needs to complete the mission while minimizing energy consumption. Half the flight's points are assigned to the efficiency of the aircraft, and the design team has worked tirelessly to create a plane that can accomplish the mission while reducing the energy required to do so. This new competition provides a unique challenge to the team, to work under strict time constraints to design and develop an aircraft with a focus on energy efficiency. With an impressive payload, capacity, and excellent range, the Albatross will become our workhorse aircraft for future competitions.
The first step in designing an aircraft is to determine the requirements and design limitations. These include things like maximum wingspan and weight and minimum payload size. From these we can come up with several preliminary designs, which we then evaluate in tools like OpenVSP and XFLR5, which are able to simulate the performance of an aircraft. Once we have the best of those designs, we can continue to iterate on it to increase its performance. We often use Open Vehicle Sketchpad, a tool originally developed by NASA, at all stages of our design, since we can quickly define and modify an aircraft as well as get estimates for drag and lift. We also use XFLR5 for analysis. However, because it does not include the aircraft's body and drag calculations, we mainly use it for analysis of the aircraft's wings. A key factor in designing the best aircraft we can is knowing exactly what we are trying to optimize. This may seem straightforward, but it becomes more difficult when we consider the many different factors involved in an aircraft's performance, and more difficult again when we consider the different ways we can measure best. For this competition, our biggest requirement can be broken up into vertical power draw, cruise power draw, and drag. Because two of these requirements are heavily dependent on the efficiency of our propulsion systems, this became one of our highest priorities, and we have gone through many different propulsion configurations in search of the best solution to our propulsion needs. Other areas that we have investigated have been lifting tails and retractable vertical motors. Of course, we also spend a lot of time looking for any reduction in mass that we can find.
Our aircraft has gone through several major redesigns over the past few months, a consequence of learning aircraft design as we go. But we have arrived at what we are happy to call version 1. In some ways, it's reminiscent of our current mainframe, albeit considerably larger with its 3-meter wingspan. It's a twin-boom quadplane with a high-mounted wing and a split tail section. This is the culmination of months of intricate back and forth design, and we are so proud to finally present to you the Albatross.
So with the conceptual design fleshed out, the next step is to design the details. These ideas now become projects. Our plan is to rapidly prototype a version 1 while optimising the design for version 2. For version 1, some of our members in aerostructures will work on lightweight, high-strength wings. This wing is wider than anything we have built before and yet must be lighter. You have heard about the Icelandic method, which we hope to use, but there are opportunities for carbon fibre 3D printing, generative design, new composite materials and much more. Other members will work on the fuselage manufacturing and aerodynamics integration. Collaboration between the aerostructures, flight operations and avionics sections will allow us to reduce manufacturing time and improve access for operation. The fuselage structure itself will be designed from scratch with a goal to reduce mass by 30% compared to our other aircraft. Also, the propulsion system will be further developed. Mentioned earlier, the thrust test stand will be vital when choosing propellers and motors to maximise our efficiency. Then, with avionics working on the camera and search system, flight controls and telemetry, the first version of our aircraft will be manufactured before the end of the year. Other projects we hope to pursue include winglets, retractable or faired propulsion systems, weatherproofing, and packaging and portability for travel to Germany. In parallel, optimisation will begin. Mass optimisation will encourage us to look at alternative battery systems like lithium-ion, but mostly to build on the rapid prototyping phase in more strategic ways. Our biggest goal, though, is aerodynamic optimisation. Using computational fluid dynamics, CFD, we plan to improve our aerofoil, our wing, our tail, and the fuselage design to reduce drag. As a team, UAS has experience in aerodynamic analysis, but optimisation is mostly done through idealised theory or trial and error. Now though, we are planning to use mathematical techniques and algorithms with software such as MDOLab, Mac Aero, ANSYS, XFLR5 and MATLAB to find the best solution, not just a better solution. We are hoping for drag reductions of up to 10%, and this could become a key component of our design process in future. In 2022, we aim to be testing the complete Albatross version 1 aircraft, while implementing our optimizations and improvements to build version 2. Testing will include performance tests in VTOL and cruise, testing of the image recognition software, full mission practice, and again, much more. Additionally, we are working towards wind tunnel testing with Monash to further improve our design and validate our CFD. More testing on version 2 will allow us to improve the design yet again for a final version 3, which we'll take to Germany. The NFC competition is pushing Monash UAS to innovate and improve on what we've done in the past. The goal is to challenge ourselves with exciting projects beyond classroom learning and build a slick plane to compete in Germany. We hope this excites you as much as it does us.
Every year, our team continues to grow in numbers, skills, and diversity. Our members come from all walks of life, and together we strive for our team's goals. In line with this, we encourage anyone interested in our team to apply and see where your UAS journey can take you. We appreciate the hard work and effort put into UAS by all 70 of our members and look forward to the contributions that everyone will bring. Monash UAS consists of members from many different backgrounds and specializations, ranging from civil to aerospace to electrical engineering, as well as commerce, arts, and design students. Together, we all bring our knowledge and unique viewpoints to the table. With this in mind, we encourage all students to apply and extend an especially warm invitation to women and other underrepresented groups in engineering. I know that many of you in the audience might be interested in joining the team, either in the current recruitment period, which ends at 11:59 this Sunday, or at a later date in a future recruitment. Talking to people one-on-one in a setting like this will be a fantastic way to get some understanding about what it's really like to be in Monash UAS.
A huge thank you to everyone who stuck around. I hope this presentation gave you all a bit of context about the team's achievements and activities. I want to emphasise this is just the beginning of our time together tonight. Our technology is one thing, but what really makes our team stand out is the people within it. Please take the time to explore the virtual space we've created for you. So not only ask questions about the projects which you've seen, but also to meet and get to know some new people. Although we still have some way to go, I am proud to see the way that our team has become more inviting and inclusive for people from all walks of life, and I hope that meeting our members tonight will confirm this for you. Now that the recorded portion of this showcase is finished, we can move on to the interactive component. We can't serve drinks and shake hands like we usually would, but I hope that you'll find this gamified reality to be the next best thing. Thank you everyone for listening. Over and out.